track with where the schedule was. We did have a bit of a scheduling issue with the clash between classes 2 and 3, I think it was, and this does get us back onto track. So this topic is going to be the normal distribution. So going back to probability type topics. So to recap, we've looked at how to handle discrete probability. That was when you have like specific quantities of things like dice rolls or coin tosses, that sort of thing. We looked at binomial, which was a subset of that, which required you to have like the same probability of outcomes every single time. So repeated trials have to be independent, and it required 2 different outcomes. Then in the last time we looked at probability, it was for continuous probability. We were looking at how to handle things that could be of arbitrary accuracy, things like heights or lengths, right? Could be 5 meters, could be 5.012 meters, right? The number of decimal places is purely determined by how accurate your measurement is, rather than just the fact that it is that specific value. What we then look at is the normal distribution, which is the most widely used, or at least widely applicable, probability density function or probability distribution function, however you want to say it. The normal distribution looks like this, and it accounts for pretty much most things that come up in real life. One of the things that comes up is your grade distribution. The grades within your cohort are likely going to be distributed normally. They're going to have some mean average value, of which most people are going to reach, and then it's going to be distributed either side of that mean based on the other people in your cohort's grades. So too will the ATAR results. So too will the study score results. I'm just using school examples, but this could describe pretty much any scenario. Like even if I describe like how far I could throw a ball, right? If I throw a ball with all my strength, it'll reach some average distance plus or minus a certain upper or lower bound. That will be normally distributed. You don't really need to know this equation, although it can help when it comes to working with normal distributions, because it tells you what each of the terms are, or at least it can help you figure out what each of the terms are doing to the normal distribution. So this is the equation which describes the shape of this curve. You'll notice there's the standard deviation term in there, and there's a mean in there as well. If you look at where the mean is located, that's basically a horizontal translation. If you imagine like other functions of f of x, right? Whenever you have x minus h or x minus something, that minus something sets your horizontal translation. In the case of the normal distribution, it sets the middle of this bell curve. Then you'll notice that there are these standard deviation terms. There's actually 2 of them, and they are in the spots which would be considered dilation factors in other functions. They're divisions or multiplications, right? Dilation factors. It also makes sense then that the standard deviation term will therefore dictate how far spread out this distribution is. So if we look at a few different outcomes, this one here, if we look at specifically the spread, the standard deviation of a normal distribution, this one here would have a low standard deviation, which would mean that it has a very tall and thin curve. Standard deviation is a measure of how far out things are spread. So if you have a small standard deviation, a lot of the probability is concentrated on one particular spot. Whereas if you have a high standard deviation, it usually means you have a overall shallower or flatter curve that is more spread out across your x-axis. That's this one here. Larger standard deviations result in a shorter, flatter curve. Smaller standard deviations result in a taller, sharper curve. Those are some fundamentals around how normal distributions differ from other continuous probability. But for the vast majority of what you'll be doing, you can basically consider this as just another type of continuous probability equation. You could still use integrals to whoops, you can still use integrals to solve the probabilities, just like you would for continuous probability. Any questions about this so far?
Oh, good.
Sweet. Okay, next up. So, how do we find probabilities? Well, as I said, you could use integrals to do this, and that's how you might do it if some of these are unknown. Like, for instance, if you didn't know the upper or lower bound, or the, well, you should know the mean and standard deviation, but let's say you don't know one of these, then you might want to consider using integrals, but that's a pretty niche example, and I don't think it's particularly likely to come up where you would need to use integrals. So what we tend to do is rely on our CAS instead. So the CAS has a function called norm CDF. That's the TI Inspire way. There's also the Casio way, which I think is called normal CDF, but it's very much the same sort of stuff. You want to give the lower bound, you want to give the upper bound, the mean and standard deviation. This is how you find probabilities in a certain range of outcomes. So this one here, if you see like a quick example of what might come up, it'll tell you that it's a normally distributed random variable. That's your indicator to use these normal distribution functions. In this case, we're told the mean and standard deviation, and you want to find the probability that our x value is between a certain lower and upper bound. So as far as how that looks on the CAS, starting with TI Inspire, menu 5, 5, and then you'll see the three normal functions: normal PDF, normal CDF, inverse normal. The one we care about for a range of values, normal CDF. You'll get a little plugin window. You'll do your lower and upper bound. In this case, it's 140 and 160 respectively. We were told the mean was 160, and we were told the standard deviation was 8. Click that in, and you get a completely different value to what's written on the thing. What did I do differently here? Okay, mean is 160. Let me just make sure I didn't put things in the wrong spot there.
The upper bound was 170. That was the mistake.
Okay, thank you. 140, 170, mean 160, deviation 8. Yeah, okay, there we go. Nice, thank you. Yeah, so filling it in properly will get you the right result, sure enough. And then on the Casio, probably better off going interactive on these. Interactive will pull up a window, kind of like what was going on there. And then this one's going to be under distribution, continuous, and then, well, you can see your two normal values there. So again, CDF is going to be the thing. In fact, yeah, looks like this one's also called norm CDF. And you can see it's a very similar setup. So once again, lower bound 140, upper bound 170. Let's not do that again. Mean 160. They have these little, oh wait, that's right. They got this back to front. The mean is in a different spot to the standard deviation on this CAS. And they have a little like window to remind you which one's which. So lower boundary, upper boundary. This one down here, population standard deviation. That's a pretty technical term, but yeah, it just has little descriptions for how you go about it. And so hit OK, and you get the same result. Yeah, that's that. Any questions on how to find a range of probabilities? Okay, next up, finding the upper or lower bound of a given probability. So this is where you're basically doing percentiles. If you remember from continuous probability, it would be an unknown upper bound or an unknown lower bound, depending on what you have. In this case, we have a normally distributed variable with a mean of 10, standard deviation of 0.8. Find the value of k for which 80% of scores are below. So one of the things I like to do when I come across this kind of question is draw a quick picture of what might be going on. It's usually pretty quick and easy to draw a representative normal distribution. You just got to get good at drawing a little bell curve like that. The center of it is going to be the mean, which is 10. Everything else you kind of just leave. Standard deviations, you could plot them out, but it doesn't really help a whole lot. And then to represent 80% of scores being below, you'd basically draw what you assume to be roughly 80% of the area. So there's the 0.8. And so what it means is if 80% of scores are below this value, then we want this value here. The way we do that is with the inverse normal function. You want to give this value, which is the total amount of area that's covered. You want to give the mean, that's this, and you want to give the standard deviation. If you give those three things, you'll get this value. On the TI Inspire, that was, I believe, the third option. And 553 for inverse normal. Area, so 0.8. Mean, we were told was 10. Standard deviation, we were told was 0.8. And so that's what we do. Giving you, rounded to one decimal place, it'd be about 10.7. Worth pointing out, on the TI Inspire, you have to go left. So what I mean by that is if my question was instead worded as find A for which 20% of scores are above, then you would have to rewrite it in a way where everything is pointing left of the value rather than right of the value. Because if I put 0.2 in a TI Inspire, what you're finding is this spot here, for which there's 20% of the area to the left. So TI Inspire, always left. Casio, finally, has something better going for it, which is that you can actually pick which direction you're aiming at. So it's under inverse, not under continuous or discrete, but inverse, and then it'll be the inv norm CDF. So you click that, and it's the tail setting that you care about here. Whether you're center is really weird. I don't know what center does, but I know what left and right do. So let's play with that instead. So if we're saying it's left, then you're going to use that probability of 0.8. Right, it's that total area that we were looking at. We were told the standard deviation is also 0.8. We're told the mean was 10. We hit enter. We're okay, I guess, sure. And that's going to give us the 10.67 that we had from before. Now, I would hazard a guess if I now do the same thing for right, and I put this as 0.2 instead, because that would be what's right of the distribution, I should also get the same value. Yeah. So, God knows what center means under that circumstance, but left or right should be all you ever need to make use of, depending on if your area is pointing right or pointing left of the value. So yeah, look at that. Casio's finally done something that's actually better than the TI Inspire case. Okay. That's about it for those. Any questions on how that worked?
Oh, good.
Sweet. Okay, next up is confidence intervals. This is specifically the topic that uses confidence intervals the most, with the exception of the next topic after this, which isn't too far removed from what we're doing. It's the 68, 95, and 99% rules, which basically tell you where the bulk of the probability of a distribution is located. 68% rule tells you that roughly 68% of the area is going to be between plus or minus one standard deviation of your of the mean, 95% between plus or minus 2, and 99% between plus or minus 3. This is the only one that I've ever seen get tested. So if you're going to memorize one of those things, do the 95% rule. This doesn't really have any applications in Tech Active unless it literally asks you like to explain what's going on here. It's more so useful for tech-free scenarios, which would be something like this. Normally distributed random variable has a mean of 100 and a standard deviation of 15. What percentage of scores lie above 115? So on a CAS, if you could, in fact, I probably have a CAS. Yeah, we'll talk about that one later then. So, assuming we have to do this tech-free, one of the things you can do is well, the only thing you can do is use the confidence interval approximations that we just had a look at from before. Now, you can draw up this pretty quick. Again, it's just the bell curve thing that I drew earlier. One of the things you would want to plot out first would be the mean and the score that you're specifically looking for. So you would put down 100 as the center, and you would put 115 as the tick that you're looking for. And you might even shade a particular portion of the graph, like I've used red to say, hey, we want all of this area that's right of this value. So what can we do from there? Well, I would first say 50% of my area is to the left of this mean and 50% is to the right. So I can say off the bat that 50% is all of this stuff. The next thing I can say is that 68% of the results are going to be between plus or minus 1 standard deviation of the mean. So 1 standard deviation is 15, which would mean that from here, 115 all the way up to 85, that area that I've highlighted there accounts for 68% of my total area. And so I think, okay, I've already accounted for that left-hand side with my 50%. So all I'm going to do is halve that 68 down to 34, and that must therefore be this right-hand side half of that approximate area. So if all of this is 50 and 34, is the addition of 50 and 34, then reminder that all the total area has to add up to 100. So all you do is you add these two things together, take it away from 100, that's going to get you your 16%. Fair enough on how that works?
Yeah.
Easy. If it's tech active, then this is a stock standard case of using the CDF function. So it told us what percentage of scores lie above 115. We want this section. So our lower bound is 115. Our upper bound is infinity. So this is one of the cases where you'll be using infinities in your upper or lower bound a decent portion of the time, which is what this would look like. Lower bound, upper bound, mean, standard deviation. And you can see, as what the CAS tells you, 0.159, it's basically 16%. So remember, it is an approximation. We've truncated a few decimal places, or a lot of decimal places. So yeah, that's what we do in tech-free. This is what you would do tech-active. That's it for fundamentals of normal distribution. So you'll see a few key things you need to be aware of for the CAS functions, and then the ability to use your confidence intervals to help out there. If you're at all curious, you can play around with the function itself and just sort of see how each term impacts things. But you don't need to know this for any question. You can always get around it in some way, shape, or form without needing it to use it. Another thing that tends to be important with normal distribution questions is the so-called standard normal distribution. So what's going on there is a lot of what we want to do is normalize our data. And that's what the standard normal distribution can help you out with. We basically take any regular normal distribution. So let's say we were using the one from earlier over here, which had a mean of 100, standard deviation of 15, and we're going to transform it in a way where it has a mean of 0 and a standard deviation of 1. That's the overall goal. We do some sort of transformation to achieve that. To represent this as its own distinct thing, instead of using x values as your x-axis, we use z values, so-called z-score values. And because the standard deviation is, or the standard deviation values are what's on the x-axis, then it follows that the z-scores are basically just how many standard deviations away you are from the mean. This here is the conversion formula. So you can go between z and x using this formula here. It does a lot more than that, but that's fundamentally what you would use it for in most cases. However, it's always worth pointing out that basically put, as long as you have 3 of the 4 variables, you can always solve for the last one. If you have z, x, and mean, you can find standard deviation. If you have mean, standard deviation, and x, you can find z, so on and so forth. You'll need to be able to use basically every version of this equation. The reason why this becomes important is because you'll come across questions like this. X is a normally distributed random variable with a mean of 6, variance of 4. So we're told mean and variance of the original distribution. And we are contrasting that with Z, the standard normal distribution. And the goal is to figure out B such that probability of x being greater than 7 is the same as z being less than b. So this is a normal distribution probability. This is a standard, a normal distribution probability. And we want to figure out what I would have to choose as my, well, in this case, it would be an upper bound that would match this lower bound, essentially. First thing I would do is try to rewrite this equation to make sure that everything's pointing in the same direction, right? Very hard to contrast an upper bound with a lower bound. And so one of the first things I will be doing is looking at my normal distribution, because that's the thing I have. Well, I guess you could do either way, really. You have all the information for normal, you have all the information for standard normal. I've specifically chosen to look at the normal distribution, which has mean of 6, as we were told. And so all we're going to do from there is plot what does probability x being greater than 7 actually look like. X being greater than 7 is all of this area. And so in order to flip the direction of that inequality, what I need to do is figure out, okay, how far is this removed from the mean? It's going to be removed by a distance of 1. And so all I do is go to the opposite direction and say, okay, this area all the way to the left is the same thing as this area all the way to the right. So in that way, x being greater than 7 is the same thing as x being less than 5, as far as probabilities are concerned. So instead of using this thing over here, I can now rewrite my equation such that probability of x being less than 5 is the same as z being less than b. The reason why that matters is because when you look at the z transform formula, we need a z, an x, a mean, and a standard deviation. We have the mean of 6. We have a variance of 4, so that means a standard deviation of 2, because standard deviation is always the square root of variance. We have our x value. That's going to be 5, because we're now pointing in the right direction. We have the 3 things. All we need to do is simplify, and that's going to solve for z. Cool with that? Tough question. Nice. Here's another example of how you could use the exact same equation. So, very similar vibe. Mean, standard normal, and then it's relating a particular probability with each other. Again, you could probably go either way. You could use z, you could use the normal distribution thing to sort of flip them around. Point being is that we've got this nastiness where they're 2 different directions, so first things first, we flip them. I'm just using a normal distribution, standard normal distribution here, just to show you that you can always use that. We always know standard normal has a mean of 0, so you're just going to add a 0 there, and you're just going to make sense of what's going on. So for instance, probability being z of z being greater than 1.5, that will be this thing. So 1 minus that is going to be everything to the left. And so we think, okay, well, instead of saying 1 minus that, why don't we just say this instead? Z less than 1.5. Makes much more sense. That way, we got two less than symbols in the right direction. We have an x value, we have a z value, we had a mean of 250. The only thing we didn't know was that standard deviation. Simplify, simplify, simplify. Standard deviation equals 6. So this is basically the equation you'll use every single time the standard normal is mentioned. Basically anything that says like, hey, here's probability z, this is your go-to. Just grab as many terms of this as you can. It'll help you with solving the question. That's it for the lecture section on this. Any questions that I should clarify before moving on to textbook stuff? In the meantime, I shall look and see what the textbook stuff is. So it's 16A to D. Okay. Yeah, there you go. Here's the, oh, where was it? There we go. Integrals. All right. So you can in fact use integrals for this. Let's just choose not to. It's a whole bunch of background information if you want to have a read as to theory, but if you just want to stick with what actually matters, then it'll be what I've covered. Let's start with some theory stuff. So question 2 here, let's just get an idea of what normal distribution even means. So when we're looking at question 2 here, which of these are approximately normally distributed? So basically A, B, or C, which ones look to be normal distributed?
Would it be C?
C? Yeah, C sounds about right to me. You've got basically a mean of, I don't know, call it 75-ish. Maybe, oh, I guess it's 70, isn't it? 70 to 75. And then everything is roughly like symmetrical about that. B is, you could maybe argue that it has a really tight standard deviation, where it's got a mean and then spread off across. But this one's a bit harder to justify. But yeah, that's pretty much it there. Let's see what else is going on. This stuff never gets tested, so we can leave that there. Transformations, yeah, okay. So, not super relevant. Yeah, okay, this will be good. Cool. So we'll do question 1. I guess it doesn't matter which of the question ones it is. We have an IQ test, normally distributed, mean of 100, standard deviation of 15. So first things first, when you're told these things, always helps to just draw a quick normal distribution. So I'll start drawing that. In the meantime, have a read of question A in there, and let me know what you might start doing to solve it in a tech-free way. And if you don't remember tech-free, maybe even tell me tech-active.
With CAS, could we do the CDF thing?
Yeah, CDF is correct. That's it. So CDF, let's give that a shot. Oh, CDF, need 553. No, not 3, but 2. All right, what do we plug in to make it work?
They provided us with the mean and the standard deviation.
Yep, they sure did. Mean 100, standard deviation 15. What else? So if we're solving A specifically,
Um, could we would the upper bound be 130?
up and down 130. Why 130?
I'm not sure because I it's like the biggest value.
It's
I
the
don't.
biggest value you're seeing there. Yeah, okay. I will say when it's these sections, like A is separate to B is separate to C. They don't have any relation to each other. But no, upper bound, if it's not specified, the value you choose is infinity, right? If it's above 1 in 15, totally unbounded, then 115 is your lower, and you choose your upper bound to be infinity. So even though it makes no sense for an IQ to be infinity, when you're using normal distribution, you kind of got to switch that part of your brain off a little bit. You can't just think, what is the biggest IQ possible? You do shoot them off to infinities. That's going to get you roughly 16%. So that's in a tech active way. Maybe if you don't remember exactly what to do tech free, do you at least remember the idea of how you would try go about it?
Would we write in 115 and then find the space that's on the left of it?
On the right, yeah, on the right of it because it's above 115. But otherwise, yeah. So you'll do your 115, and then above 115 would be all of this. So we're looking at all this area in there. The question then becomes, how do we do that? Well, that's where using our confidence intervals comes into play. So you can make use of the 68, 95, or 99% rules. So what I'll do is I'll do a screen grab of that, see if you can work one out from that. And I'll flip back to, yeah, okay, because knowing the standard deviation will be important. Yeah, knowing the standard deviation will be important. So standard, whoop, wrong color. Standard deviation is 15 in this case. So how can we make use of our approximations to figure out what that red shaded area is going to be?
Would we use the 99% rule?
99% rule, okay. So 99% rule tells us between plus or minus 3 standard deviations is going to be 99%. So 3 standard deviations, we're looking at 45 either side of 100. So we're looking at 145, and then we're looking at, what's that? So that'll be 30, no, 65, 55 out here. That's what we're basically saying by using the 99% rule, is that from here to here is 99%. What can we do with that?
I'm not sure.
That's fine. So one of the first things that's usually a bit of a gimme is any distribution, no matter what it is going to be 50-50 between the mean. So what we know is that from here and left is always 0.5. Okay. So we've already accounted for 50% of the area. We just got to make up this last little section in here, and then whatever's left over has to be this red spot. So one of the things you need to be able to do is figure out what does 115 actually mean in terms of its separations, in terms of standard deviations. Like how many standard deviations to the right is 115?
I'm not too sure what that means.
So um, basically, if I take it a step back for like the other things I calculated, when you said to have a look at plus minus 3 standard deviations, I said, okay, one standard deviation is 15, so 3 of them must be 45. So if 100 is your center, then 145 is 3 to the right, and 55 is 3 to the left. So my question to you now is, what does 115 mean in terms of number of standard deviations? So like, this is 3 standard deviations, this is minus 3 standard deviations. What's this one therefore going to be?
Would it be one?
Yeah, 1 standard deviation, correct. And so in answering that question, that tells you which approximation is going to be useful. And that's going to be the one that's the plus minus 1 standard deviation. So that's the 68% rule. So going all the way to 99 was a bit big in that case. We don't really need to use these or want to use those. What's a bit more useful is using the 68% rule. So 15 right. We don't really care what this last value is, but basically from here to here is 0.68. And so if we know that 0.5 is all of this to the left, and 0.68 is symmetrical here, then it means you've got 0.34 over here and 0.34 over here. 0.34 over here, and then we've already done all of this left, so we don't need to write 0.34 again. And so yeah, what that does is it gives us, okay, 0.5, 0.34, that makes some value to the left. Everything else is therefore to the right. So with that in mind, what must the right-hand side therefore be as far as like area? Reminder that total has to be 100%.
Would it be 0.32?
0.32. Not 0.32. How did you come to that one? Oh, wait, I think I might know. 0.32, almost. There's one thing you haven't quite accounted for with that. We just want this section, and what you've given me is this section as well. I'm assuming you've done 1 minus 0.68?
Yeah.
Yeah. So 0.68 is from here to here. Doing 1 minus 0.68 gives you this and this. And so if you remember that these are symmetrical, if you only want this, you just halve it, knock that off down to 16%. So that's one way of doing it, just knowing your 68% and then halving what's outside. Or you can do 0.5 and 0.34, add those together, and then take that from 1. Both ways work, because 0.5 accounts for all of this. 0.34 accounts for all of this. Sorry, I don't know why I did all that. 0.34 is this section here. Add those together, and then what's left over must be this. But okay, we'll do another one of those just so we can practice the skill of that a little bit more. So, exact same distribution, or at least it's supposed to look like the same distribution. This time we do below 85. All right. So 85 is here. Below 85 means we're going left or right from this point.
Left.
Left is correct, yeah. So we want to know what that is. So the first question from what we had to answer before was what does the value mean in terms of standard deviations? So what does 85 mean in terms of standard deviations?
Plus minus 1.
Yeah, yeah. So we're once again going to use our plus minus 1. So that's going to be, again, 68%. It's going to be between those two. So you might be able to tell already what the answer is going to be. That, or you can calculate it quickly. What's this section therefore going to be?
Would it just be 16% again?
Yeah, 16% again. Because that 85 was actually this. Yeah. Okay, that's good. Next up, we'll do one more just to seal it in. We'll use a different approximation. So, got the 100, and we'll do below 70 this time. So put a 70 there. Not to scale, of course. I won't say too much on this one now. I'll leave it up to you to figure out what you could do to figure out that particular area.
On the right side of the 100, it would be 0.5.
Yep, yep.
And the standard deviation would be plus minus 1.
Would it? Standard deviation is 15. So how many 15s are separated between these two?
Two.
Yeah, 2 standard deviations. So we've now got to use a different approximation. Same idea, but you got to use a different number now for your approximation. Which one is that?
95%.
Yeah, 95%. That's it. So 95% is going to be between plus minus 2 standard deviations. You can solve from here if you like, or depending on how you calculate it, you might want to figure out what this point is here, then get this, halve it, whatever you want to do for that.
I tried to figure it out, but I just got something completely wrong.
Might not be completely wrong. Did you get 2.5%?
No.
Okay, then that's a bit wrong. Okay, so there's a couple ways you could do this. If you're just using the most streamlined approach to what we've just discussed, it would be saying, okay, everything right of the mean is 50%, so we can mark that off as good. We've sorted that out. Then we say that 95 is split either side of here and here. We don't have to care about anything on this side anymore. We just want to care about what the portion is over here. So, simple question. If 95% is spread evenly between these two spots, How do I know what's just on this side?
You'd halve it.
Half it, yeah. So 95 halved is 47.5%. 47.5, well, should be a decimal, but you get the point, percent. So this section here is 50%. This section here is 47.5%. This section here is the thing that we want. Any thoughts on how we could get the red from here?
Could we add them in a -1?
That's it, yeah. 1 minus the addition of 0.475 and 0.5, which just turns out to be 2.5%. Or 0.0, also going to be 0.025. So very small number. Fair enough.
Yeah.
That'll be basically the most, yeah, probably the most streamlined way of going about it. The alternative, depending on if you like it better, would be ignoring this half stuff and just be like, okay, I know this is 2 standard deviations, so I'm using 95%. That means that 5% is right and left of these 2 ticks. I don't care about this side, so 5% halved gets you to 2.5%. That's another way of doing that. And even just saying that out loud, it is less things to think about, or at least definitely less steps, but it also means you have to be better at your spatial awareness, I think. Because you've got to be like, okay, this is 2 standard deviations, 95 is here, that means 5 is split evenly either side, 2.5 left, 2.5 right. Which of those sounds easier for you?
I think the first way.
First way? Yeah, easy. Yeah, you don't need to know both, just need to make one work, and that's pretty much it. Because either way, you're still using the same overall rule or concept. So you won't be forced to use one or the other. Cool. Okay, that's those. Question 2 might be interesting. This one's probably not like accessible, but worth discussing. Maybe we'll do like one of them. State the mean and standard deviation of what you're seeing below here. So let's say we're looking at A. This is our scale. What is going to be the mean and standard deviation involved here? This one requires a little bit of guesswork or assumptions.
The mean would just be the one that's like directly like straight underneath in the middle.
Yep, that's correct. Standard deviations where it gets a bit trickier. How do we justify that?
We could use our CAS.
How? I can't think of a way you'd use a CAS for this. You definitely need to sort of think about the proportions of the graph. It takes a bit of lateral thinking on this one. Think about how in the tech freeway we figured out how many standard deviations things were ahead or behind, and see if you can apply that to the interval ticks that you can see here.
Would it be 5?
Yeah, it's going to be 5. There you go. You can see all those values are separated by 5. There's 3 to the right, 3 to the left. The assumption is that these are all the standard deviation separations. There you go. So not super accessible, that one, but good for concept. And then I believe everything else is just going to be worded versions of solving between certain values. Like this one here, between 152, 168. If you know your mean is 160, standard deviation is 8. 168 is 1 to the right, 152 is 1 to the left. Plus minus 1, you're going to assume 68% between these two values. That's literally all this ever is. So you'll get your boundaries and you'll do it based on what we just described there. The only challenge will be how you take what's given to you in a worded scenario and then just break it down to what's mean, what's standard deviation, and then split things up here. In fact, this is a really fun one for you to do at some point. We won't do it here because it'll be pretty time consuming, but it'll be, hey, this is how we standardize marks. There's a mean mark across the different subjects, um, and there's a mark that one of the students got. Any spread of data is going to have a mean and a standard deviation. And so all you do is you take the mark that the student got, you run it through that Z calculation, and you get the standardized mark. This is how, it might be a bit more sophisticated than this, but this is fundamentally how we do things like ATARs and study scores. You take what your distribution is and you chuck it through an equation to make it what you want it to look like, spread out in a in a smoothish way. So this will be a fun exercise to see. In fact, yeah, we do actually need to practice a little bit on the Z, so why not? We'll give it a shot. So let's see here. Yeah, okay, so 13 will be a decent one to try. So the equation that's relevant here is that Z is equal to X minus the mean over the standard deviation. This is just a plug and play, but yeah. What's each of the values going to be? I don't think this is going to be too hard of a question for you.
It would be Z equals 77 minus 68.5 over 4.9.
Yeah, exactly. We're just plugging and playing, and that'll give a certain value. Easy. What would be good is it in this one that they do? Z. Where's the one where they contrast the Z and the X? Not this one. I vaguely remember these being tough. Let's see. Oh, there's even conditional probabilities in there. My God. Okay, that's going to be really strange. This one's not super accessible. I wouldn't worry about it. I haven't seen that in a question before. I do remember these being difficult though, so let's have a read. Mean of 22, standard deviation of 7. Find these. This must be tech active because that's not a single standard deviation away. 22 isn't 7 removed from 26. Yeah, these are going to be tech active. So probably D would be a good one to try and talk about then in a tech active way. Find the value of C such that probability of X less than C equals 0.95. So have a read of D there while I draw up the normal distribution there as a quick visual. Mean of 22, kind of hard to draw the standard deviation, but what we're trying to achieve is figure out there's going to be some value C such that everything left is less than, everything left is 0.95. And I'll just write standard deviation is 7 in this case. So this is a tech active version. What might we do given that we can use the CAS?
Could we use CDF?
Potentially. So let's have a look at what CDF would be. Menu 552, normal CDF. So we need to start plugging all these things in. So lower bound, what's that going to be in this case? imagine a lower bound on this distribution. What could it be? It just shoots off forever. So whenever there's an unbounded, like it's just a less than sign, there's no like cutoff. You shoot off to infinity, or in this case, negative infinity, because you're going left. Upper bound is where it gets a bit interesting, because upper bound is a letter, right? It's C. That's the unknown, and so you could put a C in there. Why not? We know the mean. The mean was 22. We know the standard deviation. That was 7. If we'd enter on this, it's not going to do its thing, right? You've got some unknown in there. Now, one thing that might work is putting this into a solve and then solving for, so what would it be? You'd have to say, make this equal to 0.95. Equal to, we're going to break it. I'm going to say less than equal to 0.95. Just because normal distribution, there's a whole bunch of decimals in there. If you say an equal sign, it's probably going to break it. Yeah, okay, that's still broken. Makes sense though. We're trying to use a function that's not particularly suited for it. The thing to use under this circumstance is the inverse normal. So the circumstances there is that you know the total area that you're trying to encompass. In this case, we do. It's going to be a total of 0.95. We know the mean, we do, which is 22. And we know the standard deviation, it's going to be 7. That's the type of function that's best suited for this. So a lot of what you do in normal distribution is just knowing what each of the CAS things are useful for. So if I just quickly point you to the screen share again, this little summary here will basically tell you, hey, here's how you do all this stuff. Norm PDF, if you want to use a specific X value, we haven't looked at that because it's very rare to come up. CDF for when you know both the upper and lower bound. Inverse normal when you know these things. So pretty much just look at the things in the brackets. If you know all those things, you can use that function. Otherwise, the function won't work. It needs all the parameters to make it work. Otherwise, yeah, these notes are of course available in the classroom, so feel free to mess around with those for a bit, or wait until your school is actually covering it. One of those. Anyway, thanks for coming. I'll stick around if you have any questions. Otherwise, take care.
Thank you so much.
Thanks.